Welcome to this problem walkthrough on Find All Anagrams in a String. In this video, we'll explore an interesting string manipulation problem that tests your understanding of hash maps and sliding window techniques. Let's dive in. In this problem, you are given two strings, S and P. The goal is to find all the starting indices in S where substrings are anagrams of P. An anagram, as you might know, is a word or phrase formed by rearranging the letters of another, using all the original characters exactly once. For example, ABC and CAB are anagrams because they use the same letters in a different order. The input format specifies that S is the string we'll search within, and P is the string whose anagrams we want to locate. Both strings will have lengths between 1 and 10,000, inclusive. The expected output is a list of integers, where each integer represents the starting index of a substring in S that is an anagram of P. The indices are zero-based, meaning the first character of S has an index of 0. The task is to generate this list of indices based on the conditions provided. Let's consider an example to clarify the problem. Suppose S is kbabakt and P is ABC. The output here should be 0, 6. Why? Because when we examine the substrings of S, we see that the substring starting at index 0, which is CBA, is an anagram of ABC. Similarly, the substring starting at index 6, which is BAC, is also an anagram of ABC. These two substrings use the same characters as P, just in a different order. Thus, the output correctly lists the starting indices of these anagrams in ascending order. Now, let's look at another example. If S is ABAB and P is AB, the output should be 0, 1, 2. Here's why: the substrings of S starting at indices 0, 1, and 2 are AB, BA, and AB, respectively. All three of these substrings are anagrams of P, as they contain the exact same letters, just rearranged. Notice how overlapping substrings are also considered, as long as they match the criteria of being an anagram of P. This demonstrates that we need to check every substring of S that is the same length as P. In another case, let's take S as ABCDFG and P as HIJ. The output here is an empty list. That's because there are no substrings of S that use all the letters in P. None of the character combinations in ABCDFG match the letters H, I, and J. This highlights an important point: if there's no overlap between the characters in S and P, or if it's impossible to form an anagram, the result should simply be an empty list. The constraints ensure that both S and P are valid lowercase English letters, and the output list must always be sorted in ascending order. When solving this problem, there are a few edge cases to handle. First, if P is longer than S, it's impossible to find any valid substrings, so the output should be an empty list. For instance, if S is at and P is ABC, there's no solution. Second, if P and S are the exact same length, we only need to check if S itself is an anagram of P. If it is, the output is 0, otherwise it's an empty list. Another case is where S and P have no overlapping characters, which would also result in an empty list. Finally, if S contains repeating characters, the algorithm must track these correctly to ensure all valid anagrams are identified. To solve this efficiently, we can use a sliding window approach combined with a frequency counter. This method avoids recomputing the frequency of characters for each substring, instead dynamically updating the window as we move through S. This ensures the solution runs in linear time, O(n), making it suitable for the input size constraints. To start, let's consider the brute force approach. The intuition behind this method is fairly simple. We generate all possible substrings of the string S that are the same length as the string P, and then check if each substring is an anagram of P. To do this, we use a sliding window of size equal to the length of P to extract substrings from S. For each substring, we compare the frequency of characters in the substring to the frequency of characters in P. If they match, we know it's an anagram, and we collect the starting index of that window. However, while this approach is conceptually straightforward, it is computationally expensive. Generating all substrings requires O(n) time, where n is the length of S, and for each substring, checking if it's an anagram involves comparing character frequencies, which takes O(m), where m is the length of P. This results in a total complexity of O(n*m). While easy to implement, This approach becomes inefficient for larger inputs due to the repeated recalculation of character frequencies for each window of the string. A more efficient way to solve this problem is by using an optimized sliding window approach with hashing. Instead of recalculating the character frequencies for every substring, we can maintain a running count of character frequencies as the window slides across the string. Here's how it works. First, we calculate the frequency of characters in P and store it in a hash map, which serves as our target frequency. Then, we use a sliding window of size equal to the length of P to traverse the string S. For the current window, we maintain its frequency count in a separate hash map. At each step, we compare the frequency count of the current window to the target frequency. If they match, we know the starting index of the window is an anagram of P. To adjust the window as it slides, we add the next character's frequency to the current window's count and remove the frequency of the character that is sliding out. This way, we avoid recalculating frequencies from scratch for every window. The computational complexity of this approach is O(m) for calculating the initial frequency of P, and O(n) for sliding the window across the string, resulting in a total complexity of O(n plus m). This optimized sliding window approach offers significant benefits over the brute force method. It eliminates redundant computations, making it far more efficient for large inputs. However, it does require slightly more effort to implement because we need to carefully manage the frequency map as the window slides. Another alternative to consider is bit masking, which can be used if the character set is small, such as lowercase English letters. Here, we encode character frequencies as a bit mask for both P and the current window, and use bitwise operations to compare them. Like the sliding window approach with hashing, this method also has a complexity of O(n plus m), but it reduces constant factors due to the efficiency of bitwise operations. However, bit masking has its limitations. It is only applicable for small character sets and can be more complex to implement compared to hashing. While it provides a faster solution in specific cases, its lack of generality makes it less practical for broader scenarios. The chosen strategy for this problem is the optimized sliding window approach with hashing. This method provides the best balance between efficiency and ease of implementation. It avoids redundant computations by reusing frequency counts as the window slides, achieving linear time complexity. Additionally, it works for any character set, making it a versatile and general solution. The key insight here is that an anagram is defined purely by character frequency, so comparing these frequencies is both sufficient and efficient for detecting matches. This realization, combined with the use of a sliding window to maintain and update frequencies dynamically, is the aha moment of this approach. While bit masking may offer a slight performance edge for small character sets, it is harder to implement and less adaptable. Brute force, on the other hand, is too slow for large inputs. Overall, the sliding window with hashing stands out as the most practical and effective solution for this problem, striking the right balance between speed, simplicity, and generality. In this problem, we need to find all starting indices of anagrams of the string P within the string S. An anagram is essentially a rearrangement of characters, so the two strings must have identical character frequencies to qualify as anagrams. The brute force approach to solving this would involve generating every possible substring of length equal to P from S, calculating the frequency of characters for each substring, and then comparing it with the frequency distribution of P. If the distributions match, we record the starting index of that substring. Although this approach is straightforward, it is computationally expensive as it involves checking every possible substring, leading to a time complexity of O(n*m), where n is the length of S and m is the length of P. To complete the brute force method, we iterate through all substrings of length equal to P, calculate their frequency distributions, and compare them with the frequency of P. If they match, we record the starting index of the substring. Finally, we return the list of all starting indices where anagrams of P are found within S. While simple, this approach is inefficient for larger strings because we repeatedly calculate character frequencies for overlapping substrings. This redundancy motivates us to consider an optimized approach. By leveraging the sliding window technique, we can dynamically update the character frequencies of the current window instead of recalculating them from scratch. This significantly reduces redundant operations and improves the efficiency of our solution. To implement the sliding window approach, we first pre-compute the frequency of characters in P using an array P_count of size 26, corresponding to each lowercase English letter. Next, we initialize a sliding window to represent the first substring of length equal to p and s, using another frequency array called window_count. After populating this array for the first window, we check if it matches p_count. If they are identical, it means the first window is an anagram of p, and we add the starting index, which is 0, to our result list. From there, we slide the window across the string by adjusting the character frequencies dynamically. For each new character entering the window, we increment its count in window_count. Simultaneously, we decrement the count of the character that is sliding out of the window. After each update, we compare window_count with p_count, and if they match, we record the starting index of the current window. The sliding window approach is highly efficient because it avoids recalculating the frequencies for every substring from scratch. Instead, it reuses the computation from the previous window, which eliminates redundant operations. By using a frequency array of size 26 instead of a hash map, we further optimize the performance since the problem is constrained to lowercase English letters. Additionally, we account for edge cases, such as when the length of p exceeds the length of s, where no anagrams are possible, or when either p or s is empty. We also handle scenarios where p contains duplicate characters, as the frequency-based approach naturally accommodates such cases. Overall, the sliding window technique, combined with frequency arrays, ensures that our algorithm is both time-efficient and space-efficient for this problem. The pseudocode for the sliding window approach begins by handling edge cases, such as returning an empty list if the length of p exceeds s. We initialize two frequency arrays, p_count and window_count, both of size 26, to store the character frequencies of p in the current window and s, respectively. We populate p_count by iterating through the characters of p, and we initialize the first window by updating window_count for the first len, p, characters of s. After setting up the initial window, we compare window_count with p_count. If they match, we add the starting index, 0, to the result list. The main part of the algorithm involves sliding the window across s while dynamically updating the frequency counts for the characters that enter and exit the window. To slide the window, we increment the frequency of the new character entering the window and decrement the frequency of the character that is sliding out. After updating the counts, we compare window_count with p_count to check if the current window forms an anagram of p. If they match, we calculate the starting index of the current window, which is len, p, plus 1, and add it to the result list. This process continues until the window has traversed the entire length of s. Once the iterations are complete, we return the result list containing all the starting indices of anagrams of p within s. The sliding window approach ensures that we efficiently find all anagrams while maintaining a linear time complexity of O(n), where n is the length of s. The time complexity of our algorithm is O(n). This includes O(m) for pre-computing the frequency of p, where m is the length of p, and O(n) for sliding the window across s. The space complexity is O(1) for the frequency arrays p_count and window_count since their size is fixed at 26, regardless of the input size. The result list requires k space, where k is the number of matching indices. As an example, consider the strings s equals kpababakt and p equals abc. The frequency of p is 1, 1, 1, corresponding to a, b, and c. The initial window, CBA, matches this frequency, so we record the index 0. Sliding the window updates the counts dynamically for each new window, and we find another match at index 6. The final result is 0, 6, which are the starting indices of anagrams of p and s. Here, we begin by importing the counter class from the collections module, which will help us efficiently track character frequencies. Then, we define a class named solution with a method findAnagrams that takes two inputs, the string s and the pattern p. Next, we calculate the lengths of these strings and store them in n and m, respectively. We also initialize an empty list called result, which will eventually hold the starting indices of all anagrams of p found in s. Before proceeding, we handle a base case. If the length of s is smaller than p, it's impossible to find an anagram, so we simply return the empty result list. Now, we use the counter class to create frequency maps. p_count will store the character frequencies of the string p, while window_count will dynamically track the frequencies of a sliding window in s as we iterate. The for loop begins to traverse each character in S, adding the current character to the sliding window by incrementing its count in window_count. If the sliding window exceeds the size of P, we adjust it by removing the character that's fallen out of range. If the count of that character becomes exactly 1, we delete the character from window_count entirely to keep the window clean and efficient. If the character being removed from the sliding window has a count greater than 1, we simply decrement its frequency in window_count. This ensures that the window always reflects the frequencies of characters within the current sliding range. Next, we compare the frequency map of the current window with P_count. If the two frequency maps are equal, it means the current window is an anagram of P. In that case, we append the starting index of this anagram to the result list. The starting index is calculated as the m+1, where I is the current index in S and m is the length of P. Once the loop completes, we return the result list, which contains all starting indices of P's anagrams in S. This implementation is efficient and leverages the sliding window technique alongside frequency counting to minimize redundant calculations, making it well suited for this problem. Here, we start by importing the necessary libraries and defining our class and method. The method findAnagrams takes two strings, S and P, as its input. First, we calculate the lengths of these strings and store them in N and M, respectively. We then initialize a result list to store the starting indices of any anagrams we find. If the length of S is smaller than P, we know that no anagrams are possible, so we immediately return the empty result list. Next, we set up two frequency counters, pCount to store the character frequency of the string P, and windowCount to track the frequency of characters in the current sliding window of S. We populate the pCount array by iterating through each character in P and updating the corresponding index. Then, we begin iterating through the string S, processing one character at a time. As we process each character in S, we add it to the sliding window by incrementing the count in windowCount for the current character. If the sliding window exceeds the size of P, we remove the character that falls out of the window by decrementing its count in windowCount. At this stage, the sliding window always represents a substring of S of the same length as P. To check if this substring is an anagram of P, we compare the array's windowCount and pCount. If they are equal, it means the current window is a valid anagram, so we add the starting index of this window, which is calculated as the m+1, to our result list. Finally, once the loop completes, we return the result list containing all starting indices of the anagrams found in S. In this example, we are tasked with finding all anagrams of the string P within the string S. Here, S is kbabakt and P is ABC. The length of P, which we'll refer to as M, is 3. To solve this, we'll use the sliding window approach, keeping our window size equal to the length of P. To get started, we initialize a few things. First, P_count is a counter object that holds the frequency of each character in P, so it's a 1, B1, C1. Then, we set up window_count, another counter that will track character frequencies in the current sliding window of S, and we initialize it as empty. Finally, we create an empty list called result, where we'll store the starting indices of any anagrams we find. With this setup, we're ready to begin iterating through the string S to look for matches. As we iterate through S, we process one character at a time. At index 0, we add C to window_count, which becomes C1. At index 1, we add B, so window_count is now C1, B1. At index 2, we add it, giving us C1, B1, 1. At this point, window_count matches P_count, meaning we found an anagram starting at index 0. We add 0 to result, making it 0. Next, at index 3, we add E to the window, so window_count is C1, B1, 1, E1. Since the window is now larger than M, we remove the character at the start of the window, which is C. This updates window_count to B1, 1, E1. As we continue, at index 4, we add B, making window_count B2, 1, E1, and then remove B from the start, returning it to B1, 1, E1. At index 5, we add it, which gives us B1, 2, E1, and then remove a, leaving B1, 1, E1. At index 6, we add C, resulting in B1, 1, C1. This matches P_count again, so we add 6 to result, making it 0, 6. For indices 7 through 9, we continue sliding the window, but we don't find any additional matches. After iterating through S, our final result is 0, 6, indicating that anagrams of ABC are found starting at indices 0 and 6. Now let's consider another example where S is ABAB and P is AB. Here, the length of P, M, is 2. We'll use the same sliding window approach. First, P_count is initialized to a 1, B1, which represents the frequency of characters in P. We also initialize window_count as an empty counter, and result as an empty list to store our results. With this setup, we begin iterating through S to find anagrams of P. As we process S at index 0, we add it to window_count, which becomes a 1. At index 1, we add B, so window_count is now a 1, B1. This matches P_count, so we add 0 to result, making it 0. At index 2, we add a updating window_count to a 2, B1. Since the window is now larger than M, we remove the character at the start of the window, which is a leaving a 1, B1. This matches P_count, so we add 1 to result, making it 0, 1. At index 3, we add B, resulting in B2 of 1. Then we remove B, giving us a 1, B1, which matches P_count again. We add 2 to result, making it 0, 1, 2. After finishing the iteration, our final result is 0, 1, 2, showing that anagrams of AB are found at indices 0, 1, and 2. The time complexity of this solution is O, n, where n represents the length of the string S. Let's break this down step by step. First, during initialization, we create a frequency counter for P using the counter function. This operation takes O, m, time, where m is the length of the string P. Initializing an empty counter for our sliding window doesn't add any significant cost. Next, within the sliding window loop, we iterate through each character in S, which happens n times. For each iteration, updating the window, whether it's adding a character to the window count or removing one that falls out, takes O, 1, since these operations involve either incrementing, decrementing, or deleting a key, all of which are efficient. Comparing the window's frequency count with the pattern's frequency count is also O1 on average, as the alphabet size is constant, limited to 26 lowercase letters. Putting all this together, the loop runs n times, and every operation inside it is O1, leading to a total cost of O(n). Now, when we sum up the costs, the total time complexity comprises the initialization cost, which is O(m), and the loop cost, which is O(n). Given that the length of P, or M, is always less than or equal to the length of S, or N, the dominant term is N, so the overall time complexity simplifies to O(n). Shifting to space complexity, the solution uses O(m plus k) space, where M is the length of P and k is the size of the alphabet. Specifically, we use two frequency counters, P_count and window_count. The size of each frequency counter depends on the number of unique characters, which is at most k, or 26, for lowercase letters. This contributes k to the space complexity. Additionally, the result list stores the starting indices of all valid anagrams. In the worst case, all substrings of S are valid anagrams, leading to m plus 1 indices being stored, which contributes n. Bringing these components together, the total space complexity is k for the counters and n for the result list, yielding an overall space complexity of n. To appreciate the efficiency of this approach, let's compare it to a brute force alternative. A naive solution would generate all substrings of S with length m and check if each one is an anagram of P. The generation step alone produces n*m substrings, and checking each substring for anagram status requires m operations using sorting or frequency comparison. This results in a total time complexity of n*m squared. In contrast, the sliding window approach is far more efficient. By maintaining a running frequency count of the current window, we avoid redundant work. Updating the window and performing frequency comparisons are both O(1) operations, making the overall time complexity O(n). Finally, let's analyze the performance across different scenarios. In the best case, the frequency counters rarely match, meaning there are minimal updates to the result list. Even in this scenario, the algorithm still completes in O(n) time. In the worst case, every substring of length m in S is a valid anagram of P. Despite this, the sliding window approach ensures that the algorithm still operates in O(n) time overall. On average, fewer substrings are valid anagrams, but the sliding window operations adding, removing, and comparing characters dominate, maintaining the O(n) time complexity. Consistently, across all cases, the time complexity remains O(n), and the space complexity, determined by the frequency counters and the result list, remains O(n) as well. When solving substring problems, it's important to avoid some common pitfalls. First, understand the difference between substrings and subsequences. Substrings are continuous segments of a string, while subsequences can skip characters. If a problem specifically asks for substrings, including non-contiguous patterns as a solution will lead to incorrect results. Next, brute force implementations are a frequent mistake, where nested loops are used to generate all possible substrings, resulting in O(n)³ time complexity. This approach is usually unnecessary, as many of these problems have optimized solutions with O(n) complexity. Another critical issue is ignoring edge cases. For example, what happens if the input string S or P is empty, or if the size of P is larger than S? Overlooking these scenarios often leads to runtime errors or incorrect outputs. Lastly, be cautious when using sliding window techniques. Forgetting to remove the contribution of the leftmost character when shifting the window can cause inaccuracies in frequency counts, especially when working on problems involving anagrams or character frequencies. Now, another common oversight is failing to account for differing character sets. Many problems may include not just lowercase letters but also uppercase letters, digits, or even special characters. Always check the constraints and ensure your solution handles all possibilities. As for solving approaches, sliding window techniques are incredibly powerful for substring problems, particularly when constraints like length or character frequency are involved. This method improves efficiency significantly, so it's important to understand both how it works and why it's effective. Hash maps are also an essential tool for these problems, especially when tracking character frequencies for tasks like finding anagrams or maintaining unique character counts. When tackling problems in interviews, it's crucial to recognize inefficiencies and optimize early. While starting with a simple approach can help you clarify your thought process, make sure to quickly transition to discussing how you would improve the solution. Finally, remember to explicitly address edge cases in your explanation. This demonstrates a thorough understanding of the problem and builds confidence in your solution. There are several related problems that can help you deepen your understanding of substring techniques. For instance, LeetCode 567, permutation in string, and LeetCode 438, find all anagrams in a string, are both great examples of problems that rely heavily on character frequency tracking and efficient window management. LeetCode 3, longest substring without repeating characters, and LeetCode 76, minimum window substring, also focus on substring operations, but with different constraints and objectives. When approaching these problems, there are multiple strategies to consider. A brute force approach is often the simplest to implement but comes with a steep computational cost, usually O(n)³, for generating and checking substrings. On the other hand, a sliding window approach combined with a hash map offers much better efficiency, typically O(n), making it ideal for problems involving constraints like character frequencies. Lastly, two-pointers are another useful technique, particularly for tasks like handling sorted strings or checking palindromes, though this method might not work universally for all substring challenges. In addition to these approaches, there are specific cases where bit manipulation can be a valuable technique. This method is particularly efficient for problems involving binary strings, as it leverages the compact representation of bits to perform operations quickly. However, its usefulness is somewhat limited to problems with binary constraints, and it's not a general solution for most substring problems. Understanding when and how to apply these alternative approaches will help you tackle a wide range of string-related challenges effectively. Great work on completing this problem. To summarize, we used a sliding window approach combined with hash maps for efficiency, allowing us to solve the problem in O(n). Key takeaways include the power of sliding window techniques and the utility of hash maps for frequency tracking. Thanks for watching, see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!